An idea very closely related to momentum and collisions is the idea of impulse. Impulse is the force acting on an object during a very short time interval. Very often, impulse is thought of as the forces acting on an object during a collision. Now, I want to be very explicit here that impulse itself is not a force. Impulse is not measured in units of newtons. Impulse has its own units that it's measured with. If I think about what happens during a collision, you could imagine two objects are moving close towards each other. They become physically in contact with each other, and then they might move off in different directions. Because those objects change their velocity, they have to have accelerated. The way you get something to accelerate is you exert a force on it. So the impulse on the object is the force exerted on that object over that very short time scale when the objects were physically in contact with each other, while they were touching each other during the collision. Impulse is designated by vector j, and the impulse on an object is the average force exerted on that object over a very short time interval. As we'll show right now, impulse on an object could also be written as the change in that object's momentum. And from looking at these equations, I could see that the units of impulse are newtons times seconds. Or I could also say the units of impulse are kilograms meters per second. Impulse has the same units as momentum. We defined the impulse of an object as the force exerted on an object over a very short time scale. So we said impulse, symbolized by vector j, is given as the average force exerted on an object over some short interval of time delta t. Usually impulse is considered in the context of some type of collision. For example, let's think of a ball that is striking the wall. So I could imagine a ball comes in, it's moving to the left, it strikes the wall, and it bounces back. Now, before the collision, the ball had a velocity and the ball was moving to the left. After the collision, the ball is moving to the right. So I could infer that the ball changed its velocity. Therefore, I could say the ball accelerated, and specifically the ball accelerated to the right. Now, to get an object to accelerate, in general, you have to exert a force on it. So in the very short time interval that the ball was in contact with the wall was exerting a force on the ball. And that force exerted on the ball caused the ball's acceleration. So we were told that the impulse is given as the average force exerted on an object times the very short interval of time. When we work with short interval of time, that depends partly on the context of the problem. The time scale of a ball hitting a wall is much longer than the time scale of an atom hitting another atom during that collision, and that's very different from the time scale of two cars crashing. So to an extent, the short time scale delta t does depend on what type of problem you're considering. So let's investigate this definition of impulse. Now, we said that impulse written as F delta t, well, if I want, I could write, using Newton's second law, I can write impulse as being equal to mass times acceleration times delta t. And we defined acceleration back in chapter 2 as the rate of change of velocity. So I defined acceleration as delta v over delta t. So if I want, I could write that in here and write impulse is equal to m delta v over delta t times delta t. And I notice I have a delta t upstairs and downstairs, so I could cancel them out. And I could write impulse as m delta v. And if I look at this equation, I could write this equation as being equal to impulse is m v final minus mv initial. And this is really just the change in momentum of the object. The object's final momentum minus the object's initial momentum, written as a vector. So in some scenarios, it will be useful for me to think of impulse as the force exerted on an object over a short interval of time. But in other scenarios, it could be useful for me to think of impulse as the change in an object's momentum when something happens to the object. Could use the idea of impulse to investigate the forces exerted on an object during a collision. One example of a collision could be thought of as a person landing on the ground. You're initially moving downward towards the ground, and then you hit the ground, you eventually come to a stop, and generally that occurs over a very short time scale. So I could think of the act of hitting the ground and eventually coming to a stop as a type of collision. In this example, let's consider a person that steps off a 3-meter tall ledge. So 3 meters, that's about 10 feet or about 1 story up. And we'll have a person, we'll say this person just steps off the ledge, so they're barely moving when they are up here. But then gravity is going to pull this person downward, and when they get to just barely above the ground, just 1 centimeter above the ground, they're going to be moving pretty fast. So to look at this problem, I first will ask how fast is the person moving just before they hit the ground. So they're going to be falling downward. We'll say up here their speed is 0, and I'll call for the moment this the initial moment, and I'll call when they're about to hit the ground the final moment. So their initial speed is 0, their initial height is going to be 3 meters up. Their final speed, we don't know what that is, and that's what we're trying to find right now. Their final height, y final, will be 0. To solve for their speed just before they hit the ground, I could use ideas from 1D motion, that would be just fine, but I'm going to use the conservation of energy because we learned about it more recently and it's just easier to work with. So I could say when the person is up here at the initial moment, E total will be equal to their initial kinetic energy, 1/2 times the mass times the initial speed squared, plus their initial gravitational potential energy, the mass times 9.8 times their initial height. And I could say when they're about to hit the ground, their total energy will be their total kinetic energy when they're about to hit the ground, 1/2 times their mass times their final speed squared, plus their gravitational potential energy when they're about to hit the ground. So I would write that as 70 times 9.8, and at this moment their height is 0, so I multiply that by 0. Now very quickly in this problem, I could see I have 0 for their initial speed and 0 for their final height, so that will make this problem easier to solve. By conservation of energy, I know the total energy up here must be the same as the total energy down here. So I could write this as 0 plus 79.8 times 3 equals 1/2 times 70 V final squared plus 0. I have 0 and 0 on both sides. I could go through the arithmetic of this, and I find the speed when the person is about to hit the ground is 7.7 meters per second. Now, as I said before, we are investigating the impulse on the person during the collision. So if we think about what does it mean during the collision, the collision occurs when the person is in contact with the ground and the ground is exerting a force on the person, eventually causing the person to come to a stop. So I am going to relabel my notion of initial and final. This is the picture of the person just before they hit the ground. So if I think of the act of hitting the ground as the collision, this is immediately before the collision. So I am going to call this moment when the person is moving downward at a speed of 7.7 meters per second, about to hit the ground, the initial moment. And at this moment, the person has a speed of 7.7 meter per second. And after the person hits the ground, eventually in a very short time interval, they come to a stop. So sometime of short time later, that person is not going to be moving. So at the final moment, V final is equal to 0. I basically relabeled my notion of initial and final. The final moment of the first part of this problem is becoming the initial moment of the next part of this problem. Okay, so we are told that impulse written as a vector could be written as F average delta t, or it could be written as the change in an object's momentum. So I could ask myself, do I know the force exerted on the person by the ground? Do I know the time interval, how long it takes the person to go from moving to a complete stop? Well, I don't really know either of these. Do I have enough information to find the initial and final momentum of the person? Yes, I do. I have the person's mass. I have the person's final speed. Now, the one thing I'm going to mention with using this equation is, remember, momentum is a vector quantity, so direction matters, positive versus negative. So I could write the impulse of the person in the y direction as P final y minus P initial y. Because impulse is the change in momentum, final momentum minus initial momentum, and we are only really caring about the vertical, the y direction. So, what is the person's final momentum? Well, the final momentum of the person is going to be the mass of the person times the final velocity of the person. So the mass of the person is still 70. The final velocity of the person in the y direction is 0. And remember, be careful with positive negative signs when you're dealing with the change in a quantity. So this is the person's final momentum minus the person's initial momentum. Their mass before they hit the ground is 70. And their velocity is going to be negative 7.7 in the y direction. They're moving at a speed of 7.7, but they're moving downward, so I do need to account for this negative sign. So I'll have negative 7.7 over here. And if I plug these numbers into a calculator to find the impulse exerted on the person, I find the impulse is going to be 539. I get a negative times a negative, that gives me a positive. And looking at the equation, impulse as change in momentum, I could infer that impulse will have the same units as momentum. So impulse will have units of kilogram meter per second. And this is the impulse in the y direction. I am writing it this way just because impulse is formally a vector quantity. The person is not moving left or right at all, so I could also say Jx is going to be equal to 0. To investigate the force exerted on a person when a person lands and allows their knees to compress, compare that to when a person lands with their knees locked, we are going to use the other equation for impulse. So I could say impulse is equal to the force exerted on the person times how long it takes that person to go from moving downward at this speed to coming to a complete stop. I know the impulse on the person is 539 kilogram meters per second. So if I find how long it takes the person to come to a stop, I'll be able to find the force on that person. So how can we go about finding that? Well, let's think back to chapter 2, 1D motion. In 1D motion, we said that if an object is undergoing constant acceleration, we could write equations like y final equals y initial, v naught yt, 1/2 ayt squared, and we had equations like vy equals v initial y plus ayt. Now, to find the time that it takes a person to go from moving to not moving, let us think of it in this way. Let's rearrange this equation to say ay is equal to vy minus v naught y divided by time. And then I could plug this term in here, and then I go through some magic and I will get the time it takes an object to go from its initial position and velocity to the object's final position and velocity is given by this. To determine this, just take the equations for 1D motion under the assumption of constant acceleration. You could take this equation for velocity, rearrange it, solve for acceleration. Take this acceleration, plug it into the acceleration up here, go through some algebra, and this is what we get. So let's think about what we have right now. If we assume that the force on the person is approximately constant, which isn't an ideal approximation, but it's not that bad either, we know the initial and final velocity of the person. Initial velocity is negative 7.7, negative because downward. Final velocity is 0. And we could say we know the initial and final position of the person. When I land, I hit the ground, then I compress by 1 centimeter. So I could say my initial position is 0 and my final position is negative 1 centimeter. Or I could say I land, I hit the ground initially at a height of 0, then I allow my body to compress 50 centimeters. So in that case, my initial position would be 0 and my final position would be negative 50 centimeters. So if I first consider I will allow my knees to compress, I could say the initial in the y direction is negative 7.7, v final in the y direction is 0. I was initially moving downward, but now I stopped moving. I could say my initial position in the y direction, I'll just write as 0. And then my final position in the y direction, I'll write as negative 0.5 for 50 centimeters below where I was when I hit the ground. So let us determine now the force on the person's knees when the person lands on the ground and their knees compress. So to do that, we could write that the impulse on the person, J, is equal to F delta T. The impulse we found previously in this problem, that is that 539 number. The force on the person's knees is what we're trying to find, and the amount of time it takes the person to go through this collision is given by this. So I could write that as delta t is 2 times y final minus y initial, so that would be negative 0.5 minus 0. And then divide that by v initial y plus v final y. V initial y is negative 7.7 and v final y is 0. And if I put these numbers into a calculator, I find that the force on the person when they land and allow their knees to compress is going to be force equals 4146 newtons. I want to compare this force exerted on the person's knees when they land to the force exerted on a person's knees if they land with their knees locked. So we will now look at the knees when they are locked. The initial and final velocity of the person are not going to change. You're still moving downward at 7.7 meters per second before you hit the ground, and after you come to a stop, your velocity is 0. However, now you compress a lot less. You hit the ground, you're at a height of 0, then your knees compress by about 1 centimeter. So this would be a y initial of 0 and a y final of negative 0.01. We could perform the exact same analysis. We could say the impulse, the change in the person's momentum, is still going to be 539. But now the force exerted on the person is going to be a lot more because the time interval is going to be much shorter. We made the time interval smaller. We need to make this force much larger to compensate. So I could write the time interval as 2y final minus y initial. So I'll have negative 0.01 minus 0 divided by v initial plus v final. V initial is negative 7.7 and v final is 0. We find that when a person lands with their knees locked, rather than landing and allowing their knees to bend to absorb the fall, the force exerted on the person is about 207,300 newtons. So the force exerted on the person's body is about 50 times greater than when they allow their knees to bend to absorb the fall.